Recording in progress.
Good morning again, and welcome to today is March the 9th. There was a change in the date for the assignment that was for you guys. I already posted it on Canvas. So the assignment is not due, I think, this Friday, but rather it's due next Tuesday. So please make sure that you do that quiz that is on Canvas and submit it on time, okay? So that is one thing. The purpose of today's lecture is on heat transfer, and what you're looking at is actually an engine that is running using ice. And the cup below, actually, it's full of ice, and this one is extracting heat from the air on this side and transferring it to the ice on the bottom. In doing so, it's moving basically the piston. I don't know if you can't see it because it's below the surface in here. If I move it slightly, you're going to see it. It's in there. Okay. And in doing so, it's causing the rotation in here, the motion of this wheel. Okay. So that's how an engine works in general, by transferring heat. So we need to understand the process, and that is basically the purpose of today's lecture. Okay, so this is the last. Let me share with you the screen. I can let this running until the ice melts, basically. Let me share with you the screen. So this is chapter 7. This is the last chapter from this group of chapters 1 through 7 that you're going to be tested on. The review is going to be available this Thursday for the exam. So as I said before, please take care of the review as much as you can, because first of all, if you don't, you're going to lose unnecessary points for nothing, for not participating. The review is some sort of a questions basically where you answer them, and it's going to mark you right or wrong. So basically one way of doing it is just basically quickly going through the entire review, which is made up of 240 some questions. And then once you submit them, you're going to see the correct answers, and then you can prepare for the exam. If you do that, you're going to get the full credit for it. That means that you have done your review. If you don't do it, of course, you get no credit. That means you did not prepare for the exam, which you're taking a big chance with it. Hopefully you don't do that, okay? Hopefully you're preparing seriously for it, okay? So that is in terms of what's coming up in the exam. And then the other thing also is chapter 8, which was, oops, the engine fell because the ice is so slippery, okay? And it broke. I have to fix this. Sorry. I'm gonna do that some other time. Or should we do it now? It's no bueno. Okay, I'll have to fix it. Okay, so it's still working. Hopefully it's still doing the trick that it was doing earlier. As long as there is not too much friction, this thing should go. But if there's too much friction with it, it's going to cause, you don't have enough energy for it to overcome it, basically. Anyway, I think we are running slow. Okay, I have a lot of toys in here. I have so many things that always. Okay, so let's continue with the heat transfer because it's an important topic. Let me do something in here because probably you're going to see it die, and that might kind of disappoint you a little bit because you probably don't want that to see it. So where is the camera? Change cameras, this one. Okay, good morning again. Okay, so we're looking at chapter 7, which is on heat transfer. This is a big topic, by the way. It's one of the most important topics in engineering because you deal with this problem sometimes in a fashion that is actually undesirable, in a sense. You don't want heat transfer because, like, for example, if you have an engine, inside the engine there are moving parts, and moving parts cause friction, and this friction causes this material actually to temperature to increase, and if the temperature increase, they start actually melt and fuse with one another. And this is one of the things that we're going to be discussing at some points in here, which is the melting and freezing points for materials. So this is an undesirable. So what you would want to do then is actually extract that heat. Usually what you do is oil for it. And that is basically what the purpose of those different kinds of engine oils, transmission fluids, and all of these things. Sometimes it's a desirable thing in a sense that, for example, for the engine back again, you would want to produce enough heat for the pistons to actually start basically moving. And when they do, they turn the flywheel, and the flywheel will turn all kinds of other moving parts in it. So that at the end, the wheels start. So again, heat is an important concept that we deal with. One of the confusions, and hopefully you guys have already resolved that, is the difference from the previous chapter. Heat is not temperature. They are not the same. Temperature is a measure of the average kinetic energy of the particle of the system, whatever it is. If it's a gas, it's a gas. If it's a liquid, it's a liquid. If it's solid, it's solid. How fast they jiggle, how fast they move in a random fashion. We don't mean kinetic energy because, for example, if I take this ball and I move it up and down, it has kinetic energy. But this is a uniform kinetic energy. This will not add to the heat of this mass. However, if I look at it with a microscope, the different atoms in here, they're moving in a random fashion, going every which way. Because the kinetic energy is proportional to the square of the velocity, this has a net value. It's not like the momentum, because if one particle goes this way and the other one goes in the opposite direction, the net momentum is zero. So the momentum in here, because this one is not going anywhere. So if it has a net momentum, it's going to go somewhere one way or the other. But the kinetic energy is not the same. Kinetic energy is the square of the velocity. So it doesn't care about the sign, which way this atom is moving and which way the other atom is moving, as long as they are moving. So in this case, since you square the number, it's going to have a net value, and that net value is actually equal to its temperature, basically. Basically, its temperature. If I take this one and put it on a furnace, for example, on a heat, well, to pump heat into it, that heat will increase temperature, making the atoms and the molecules move so fast that if I take a thermometer in here and connect it to it, the thermometer itself starts to jiggle faster and faster, and then expands and give me new reading for the temperature instead of the room temperature. So that is basically what the temperature is. Heat, on the other hand, is a form of energy. When you light a match, what happened in this case? There is a chemical reaction, and that chemical reaction takes the chemical bonding between the different components, for example, of the organic matter in this case, or even non-organic matter, and breaks them. And when they do that, they release energy. Okay, that energy, you can see it in the form of basically that flame, which is something else, which is actually a plasma state in this case. That is something that we're going to be exploring down the road. So again, that radiates energy in all kinds of forms. One of the forms that you will see is the radiation itself. That is the light that is coming out. That is basically different frequencies that emerge from it, and you see. Energy, heat, is transferred in one of three and only three ways. Okay. Conduction, like in the example before, when I had this machine was in connection directly with the ice. So in this case, I say there is a conduction. The heat is transferred by basically the electrons of this metal with the electrons of this ice. Okay. So in this case, when I touch them, there is an exchange of energy using the process of conduction. Okay. There is another process that heat is actually transferred with called the convection. Convection, like for example, in this case, the air that is touching this ice is going to move because now it's colder, so it's denser, okay? So it's going to move and it's replaced by the air that is lighter because again, that is how the process works. If you look at the soup when it's boiling or the water when it's boiling, those bubbles that are forming actually is the motion of the different particles of the air, the volume of the fluid, in this case, water, to go from high to low, and they take with them the energy in the process, the heat energy in this process. So this process is a very important process in the weather phenomena in general. It's important in fluids in general. It's important also in the core of the earth, because between the core and the earth and the mantle of the earth itself. There is a whole layer where heat is extracted from the core of the earth and basically moved to the mantle, and then it cools down up in the mantle, and then it falls down through this process that is cyclic. Of course, it takes a long time for the earth, but that's basically how the earth resurfaces basically its upper layer, okay? And then also it's important for the sun. The sun is made up of different components. One of them is the core, where the nuclear reactions are happening. That is where the hydrogen is basically fusing to make helium. And then the upper layer of the sun that we see, okay, that gives it its color. Between that, there is a huge area where heat is transferred actually between the individual, which is mainly helium and hydrogen, that are cooler on the surface of the sun, which is only about 5,500 Kelvin, which is super hot. I mean, you cannot stand on it, but it's a lot cooler than several million degrees, 10 to 20 million degrees in the core. So it's a lot hotter. So what happened in this case, the cooler will fall, the hotter will rise, and then you have this convection. So convection is an important process also in transferring heat from a hot source, which is the core in the case of the sun, and the cooler surface, which is in this case the surface of the sun, in the process. Otherwise, we would not have heat. Finally, there is radiation. Radiation is what you see in the flame actually coming out, different lights, colors, okay? You take, for example, a piece of iron and you warm it, and you will see its color start to change. It's going to be dark red, then red, then if you heat it, if you keep on basically warming it, adding heat to it, it's going to start to change to yellow, to white color, in which case all the colors basically of the spectrum are coming out. And if you continue doing that, you're actually going to get into higher and higher temperature, and it becomes blue. If you look at the flames, for example, if you have a gas, propane, for example, or methane, for example, gas that is in your household, and look at the color of the flames. They're not actually this color. Let me write this thing. Okay. Oh, did you go dark? Man, that's bad. Let me get a good flame coming out. Okay. So you see here, this is more of, at least the way it looks like to me in here. I don't know how you're looking at it. Probably you're looking at it more like white, but it's yellow, really. Yellow, orangey thing. If you look at the flames from the gas stove, it's going to be about blue color, okay, indicating that that's actually running a lot hotter than this one, okay? So then matches. Okay, that's basically what we're going to be learning in terms of radiation. The color of the flame indicates the temperature. That is basically an important concept. If you go tonight and look at the sky, look at the stars, don't look at the planets. Don't confuse the planets with the stars, okay? I know Mars, I mean, what is it? Jupiter and the moon and probably Saturn and Mars also, they are rising early in the morning. If you go at night, like in the evening, you're gonna see a lot of stars, a bunch of stars. Actually, is this, I think the constellation Orion is visible nowadays. Look at Orion, look at the shoulder of Orion, you're gonna see Betelgeuse, it looks orangey in color. Whereas Rigel, in the bottom of it, if you have binoculars, you can look at it, and I have some binoculars in here somewhere. If you look at it, it's going to be more of a bluish color, indicating that Rigel, which is in the bottom right of Orion, is going to be actually a lot hotter than, for example, when you look at Betelgeuse, which is on the opposite side of Orion. Okay, so that is something that we know about the stars. Even we never went to any of them. Actually, as a matter of fact, we didn't even go to the sun, let alone to any star. We can tell its temperature just by looking at its color. Isn't that amazing? We know a lot about these things just before going there. So there's three things in here: how heat transfers, and the temperature, and how they are related to it is a critical thing that we need to learn about, because it teaches us a lot about things. So the first idea, let me first of all connect with all of the topics in here. The fourth thing that we're going to learn, actually, after we learn about the three ways for how heat transfers, is Newton's law of cooling. Newton's law of cooling basically states the following. You take a cup of water that is hot, or like this one that is frozen, actually. It's 0 degrees Celsius. In the environment right now, the temperature is about 20 degrees Celsius. So the gradient in temperature is between 20 and 0. How fast this will cool depends on that gradient. If the outside is super warm, if I take this cup, for example, and put it on a hot day, for example, in noon, it's going to cool faster than if I put it in a colder environment. If I take this same thing and put it in a refrigerator, which is sitting about 10 degrees Celsius, it's going to take a long time for it to cool down. In the refrigerator, to warm basically in the refrigerator and become 10 degrees Celsius. Then if I put it outside, for example, when the temperature is 32, 34 degrees Celsius on a hot day, okay, in mid-July. So again, that is something that what Newton's law of cooling is. The other thing also that matters is the amount of stuff. If I take a small ice cube, for example, and put this one by itself and this cup by itself, which one do you think will melt faster? The cube by itself or the cup by itself? Or the whole cup?
I would think one by itself.
The one by itself, so the amount of basically matter in here also matters when it's cooling. So that is also part of the Newton's law of cooling, okay? So that is basically what this law is talking about. We're going to talk about the climate change and the greenhouse effect, which is something that is real, okay? And how basically radiation comes from the sun. One thing I forgot to mention, and we're going to go through these details, is conduction and convection require material for it to travel. They require a medium, they require an object. For conduction, you have to have contact between two, electrons basically are the ones that are responsible for it. Convection, on the other hand, requires gas or fluid or something in it, okay? So there is material in it. Radiation, no, it can travel in empty space. Case in point, the sun radiates energy, and that energy is just basically pure energy that comes in empty space. No charges that are bringing the energy, no matter that is bringing the energy, just basically pure energy by itself. The reason why you can see stars a lot, although they are, an incredible amount of distance away from us, is because of radiation. The energy they emit in every which way direction that you can think of, and one of them comes to us. That's why we see them. So that is a key difference. Without radiation, everything will be dark. The entire universe basically cannot see anything, including the sun. So even though the sun probably is making a lot of energy, and if it does not radiate that energy outside, we will not see it. Okay, so that is a key thing in here between them. So again, the greenhouse effect is that this radiation comes into Earth, and it comes in all kinds of wavelengths, all kinds of colors, basically, including colors we can see, namely the ultraviolet radiation, which is super energetic radiation, and the infrared radiation, which is super low, basically energy, but very long wavelength radiation. Like it comes to Earth, hence the Earth. Then basically the Earth absorbs that radiation and heats up, basically warms, and then emits it, and emits it just specific in a specific wavelength, or range of wavelength, okay, which is the infrared radiation, okay? That is what you feel heat. If you touch somebody, what you feel is the infrared radiation. If you take goggles, those goggles that hunters use in the night to see with, they're actually using infrared radiation because night is dark, but if an animal is warm compared to the dark, you can see, or a person is warm compared to the dark, you can see them because the glasses that you have them can see that kind of radiation. So again, the Earth now it's warm, it emits radiation up into the atmosphere, but because of the gases, especially carbon dioxide and water in the atmosphere, they reflect that kind of long wavelength radiation back to the surface of the Earth, which means that this energy, instead of radiating outside and basically cooling the Earth, is going to come back to warm it again. And that is basically the essence of the greenhouse effect, which is a useful effect in a sense if you do it in greenhouses where you try to grow tomatoes and pepper or whatever you like to grow your food, but it's not good for the entire planet because that can cause problems, okay? That can cause warming of the entire planet because the temperature basically will rise and rise and rise. Heat transfer and change of phase, again, this solid water H2O, if I raise its temperature above 0 degrees Celsius, around 4 degrees Celsius and above, it's going to melt and become liquid. As a matter of fact, I don't know if you see it or not, in the bottom of the cup, actually, there is some liquid part of it that started to form, okay? I had them pure ice when I started with this one. So this is what we mean by melting. Freezing is the opposite. If I take this one and put it in the refrigerator, it's going to become solid. This is phase transformation. If you take this much and warm it all the way to 100 degrees Celsius, it's going to go through another phase transformation, namely becomes a gas, okay? If I raise its temperature further or do play with its energy a lot, put it, for example, in front of different voltages, I can ionize it, actually. I can basically take the H, dissociate it, actually, the H by itself and the O by itself, and I will have hydrogen and oxygen separated. And then if I raise the temperature further, I can actually yank the electrons out of the materials. And basically at that point, I have a new state, which is a plasma state that I mentioned, okay? Plasma state is pure, basically ions by themselves, okay? So that is basically the phase transformations. And those are the main phases that we talk about. Usually the main phases are solids. Below a certain temperature, almost everything is solid. There are exceptions to this rule. And then below certain temperature, above that temperature, that same solids can become liquid. Then below certain temperature, that liquid stays liquid, and then it goes to a gas state. And then above a certain temperature, you have the so-called plasma state. So those are the 4 states of matter that I want you to at least state in the discussion item, okay? So the 4 states are solids, liquids, gases, and plasma. When I say plasma, I don't mean the plasma that the medical community talk about for the blood and all of that, okay? We mean it's basically ionized matter, okay? So those are the 4 states. So again, can I write in here? Solids, liquids, gases, and plasma. Okay, in this order, basically, usually transformation. When you are warming, you go from solid to liquid, liquid to gas, gas to plasma at some points, okay? And when you cool down, you go back in the other way around. So this is what we mean by phase transformation, okay? So that is basically every material goes through that, or most of them actually do that, not all of them, especially in terms when it comes to the last stage, which is going from solid to liquid to a solid, okay? Out of this 4, which one do you think is the most dominant form of energy in a form of matter in the universe? Which one, there is more of it in the universe than any of the other 3? Guys are typing. Okay, somebody thinks it's a gas. Allison. I mean, Alyssa. Sorry, Lisa. Get the last name. Anybody else wants to take a guess?
I'm gonna guess it's maybe solids because there's matter, and if they didn't have like a atmosphere, then there'd just be the vacuum, which is not gases, they're really liquids.
Okay, that's a good guess. I mean, if somebody guesses something based with reasoning, thinking that because we're surrounded with solids, so solids probably is a good guess. Alyssa thinks that it's gas rather more dominant than how about liquids? Anybody taking liquids or plasma? Any chance with the other 2? Come on, guys, wake up. Just a guess. You don't.
Yes.
Sorry.
Yes. Yes.
Which one did you say, Sapida?
Gas in the form of the liquid.
So gas also, Sapida thinks it's gas. Anybody else? I want somebody to be courageous enough and pick up liquids or plasma. Maybe, okay? Or we're thumbing them down, okay? Both of them, okay? Okay, let me give you a hint, okay? It's not liquids. That is the most important form. So I agree with you guys. So that is not liquids. For those who are hesitant and not qualifying liquids as one of the most dominant form of matter, I think gas is probably the second, maybe, okay? The reason why I say gas is the second, because if you look at the entire solar system, for example, gas is really a big component of, for example, of Mars and of Jupiter and Saturn, which make up the vast majority of the entire solar system. Add to them Neptune and Uranus, and both of them are gas also. So the Earth and all of those tiny things, they don't count whatsoever. Okay. So I think gas, it qualifies as number 2. Okay. Which means that solids are actually not number 1 at all, because if they cannot be more than gas, which is number 2, so it's not gas. Liquid is, forget about it. So which one is the number 1 then form of matter?
Solid.
Okay, somebody, I'm sorry?
Solid.
Plasma, you said?
Solid number 1.
Solids is not. Solids are a lot less than a gas. Look at the solar system, for example. The planets like Earth and Mars and all of that, they're very tiny compared to the 4 giants, to the 4, to Jupiter and Saturn. So solids is not definitely the biggest amount. Solids and liquid, they rank very far behind, okay?
Oh.
Okay. So and plasma and gas is not number 1, it's number 2 probably. And somebody already suggested the plasma. Okay, plasma is actually the number 1 amount of matter in the universe, because think about the stars. 99% of the solar system is actually in the sun, and the sun is plasma. So if you think of all of the solar systems out there in the universe, where their stars are the vast majority of what they make up of, so plasma is actually the number 1 by far. Okay, there is not even a single shred of a doubt. There is not even a comparison. Okay, so plasma is the number 1. I mean, probably there is that debate about the interstellar gas. That's why gas, maybe. So gas and plasma, maybe plasma. Okay, we stick usually with the word plasma. Gas is close second, if not far second. But the other 2, forget about them. Liquids and solids. Okay, so that is item 1 of the discussion. You're supposed to list them and recognize the fact that plasma is the number 1 form of matter in the universe. Okay, maybe followed by gas. That's it. Okay, so we're going to talk about boiling and melting, basically from practical perspective and what we do them on Earth, and energy and change of phase, basically how we go from phase to phase. Again, the conduction, convection, and radiation, we talked about them. Conduction is transfer of internal energy by electrons and molecular collisions within a substance. So again, you really have to have contact between them. If you take your spoon, for example, and put it on the soup and watch from the other end, one end is getting warmer and you will feel the heat coming to you, okay? If you have a window, for example, or if you have in your wall, for example, the outside is super hot and the inside is cool because you have an AC running, then the heat ultimately will come from outside to inside via that wall, okay? You have to really have a good insulating wall to minimize the effect. You cannot cancel it. It's always there, okay? So that's why we go to Walmart or Home Depot or somewhere, I mean, not Walmart, Home Depot or Lowe's or some of the stores to get those insulating materials as much as possible to keep the inside of the house cool in the summer and hot or warm in the winter. You don't want heat to basically escape when you're warming your place and then the outside is super cold. So that is basically the process of conduction. Again, depends of the thickness. The thicker the wall, the less the conduction is. So if you want really conduction, you want to have a thin wall. That's number 1. Depends on the material of the wall itself, okay? If you make it out of wood and some of the insulating materials is going to be better than if you make it, for example, out of iron or steel. You have a house made out of steel. If it's cold outside, it's going to be super cold inside. If it's warm outside, it's going to be super warm inside. So you don't want that. That's bad, okay? So that is really the process through which heat is transferred. So it depends on the material, the thickness, and also the area. So those are what matters in terms of the conduction in this case, okay? Again, conduction occurs predominantly in solids where the molecules remain in relatively restricted location. When you stick a nail into an ice, does cold flow from the ice to your hand or heat from your hand to the ice? okay? It's always flowing from the hot to the warm to the cold. So if you put your hand on the nail, you feel cool, you feel colder because of the fact that heat is being drained from your finger through the nail to the ice. And if you watch the ice, it starts to melt because its temperature is increasing. Your temperature, on the other hand, at least on your finger, is decreasing because of the process, because of the heat that is being extracted, namely the electrons, the molecules that you have in your finger starts to move slower and slower, causing the kinetic energy to be less and less, causing the temperature to be less and less, and you feel it actually, okay? You feel it in your finger, okay? If you do that experiment. So the heat always is being extracted from the hot source to the cold cold source. If you do the process backward, if you take, for example, a hot boiling soup, and you put the spoon on top of it or the nail on top of it, and you watch what's going on, in this case, you feel warmer because of the fact that heat is being extracted through the nail, from one end to the nail to the upper end of the nail where you're in contact, and that actually causes your finger to start, the molecules in your finger and the atoms in your finger to start to move faster and faster, resulting in an increased temperature, okay? And you feel it actually, okay? You feel that. So this is basically what's going on in this case.
Sir, I have another good example for that.
I'm sorry?
I have another good example for that. When we are wearing a bracelet of gold in our hand and doing something that connected with heat, we feel heat in our hand.
Yeah, because of the metal basically is a good conductor, especially gold is actually one of the best, if not the best conductor ever, okay? Take it back, I'm sorry. It's not the best conductor ever. It's the best conductor that you find in nature, okay? We can make better conductors than that, but that's basically which makes you think, Sapira, why can't we make the wires at home for the plug made out of gold instead of the copper?
Because it's so expensive.
Yeah, imagine you have your house run with gold instead of copper, okay?
Stealing me.
Don't want, okay, it's too expensive. Then that is actually okay. So, but that's a good point. Okay, thank you. Okay. Again, all of these are examples on conduction. So conduction doesn't prevent the flow of internal energy, slows the rate. So insulation, again, if you go to Home Depot or Lowe's and you would want really to insulate your house, and you get some of those best insulators, and you go to the guy and tell him, okay, I have a problem with heat at home. When it's cold outside, for example, in the winter, it gets super cold at home, although the the heater is running super high. And in the same thing, in the summer, it gets super cold also. It gets super hot, despite of the fact the AC is running super high. So I know I have some leaks, I want to fix them. Can you give me a good insulator? Okay, that is going to prevent that for you. I can guarantee you no heat will escape. That's a lie. So heat will always escape from the house in the winter or enter to the house in the cold in the summer, because there is no such a thing of a perfect, basically, insulator. There is always somehow conduction, okay? So it doesn't prevent the flow of internal, it slows it down. That is the key, okay? Make it slower. Usually for engineering, there is a process in this case. You would want to have an optimal solution. You would want to have something that balances cost versus what you really want to achieve. Exactly the same point that Sapira raised earlier. If we're going to make a house made out of copper, that instead of copper made out of gold, that is too expensive and too costly to do just to generate some power to arrest the light bulb. That is not efficient. So probably copper is a lot cheaper and better. So again, in the same fashion here, materials that are used for insulation, again, they have a lot of requirement for them, okay? You don't want to spend a lot of money just to insulate your house, because probably you just probably put another blanket and maybe you're in better shape than just going through that hassle. Again, rock, wool, and fiberglass. Fiberglass is exactly what is used. Wool, for example, is also a good insulator. That's why animals apparently learned that a long time ago and do that, like bears in the North Pole and all kinds of animals use that. And in the summer, it becomes too hot, they shed it and basically they walk without it, okay? So again, this is a trick that some animals apparently I don't know if they took Physical Science 1 to do that, but apparently bears learned that a long time ago. Okay. Okay, anyway. Snow patterns on the roof of the house show areas of conduction and insulation. Okay. So in this case, basically there is a pile up in here of ice because this place in here, there is metal in it that's cooler. So the ice in here is piling, whereas in here there is an insulation. So the heat in here is it's cooling it down. Okay. So bare parts show where heat from inside conduction through the roof and melts the snow. Again, you can just trace where the phase where the ice has changed phase. Okay. So again, it slows down the heat, the transfer of heat from the inside to the outside. Good conductors composed of atoms with loose outer electrons. Basically, the electrons can move like metals. Metals are good conductors. And usually when they're good conductor of heat, they're also good conductors of electricity too, because of the same reason, okay? All metals to varying degrees. Of course, some of them are better than others. Iron actually is a poor conductor, but it is a conductor nonetheless, okay? Copper is a good conductor of electricity and heat. Silver is actually even better. Gold is even better than the first two, and so on and so forth, okay? So that is basically, aluminum also is a conductor. It's a good conductor. Those are some of the household, basically, metals that we see on a regular basis, okay? Poor conductors delay the transfer of heat, known as good insulators, like wood, wool, straw, paper, styrofoam. And one of them, which is important, is air. Air actually is a good insulator too, to some extent. That's why it's used actually in thermos, for example, to keep your coffee warm when you put it in. There is an insulation usually of air just between the inner and the outer, basically, layers, and the coffee stays in there for a long time, basically warm, okay? So air actually is a good insulator, because if air is not good insulator, I have the plug in there that has electricity in it. So if this air is not a good insulator, I basically would be electrified. So the air is actually good insulator. And any insulator for heat is actually something good insulator up to a certain point. The trouble with the air when it comes to heat is there is a convection. When it's warm in one place, it's going to come and carry the heat to another place and basically do the cycle over and over again. That's why if you really want to have a heater in your home, you probably would want to place the heater in a higher place so that the air will circulate. Whereas if you want to have the AC unit, you would want it to have it in the bottom so that it goes and rise, so that the cool temperature the cool air doesn't stay on the top in there, okay? Again, just to help the flow of the air, use basically the convection process. Okay, this is one of the authors of the book. He walks on red hot coals because the coal actually is an insulator, okay? As long as you work fast enough, you're going to be fine, okay? Okay, again, this is the convection. We talked about it. It's this process basically where the gas rises. You can actually visualize it actually and see it rising, okay, in the air. If we have a cool enough night, day, we could actually do this experiment and you see actually what looks like some fume basically coming out from the heat, okay, or the cold in this case, okay, rising. And that is actually processed through the convection. What is rising in this case is gas. People thought that that was actually the heat itself rising, and they called it the fluid, the calorific fluid. So they gave it a name, okay? They thought that some sort of fluid. Either you have it or you don't have it. That's what they were thinking. But it turns out it's just the fluid in this case itself that is rising to cool down, and basically, and the process reverses. Okay. Here is an example. You can do this at home. Please don't get your hand very close because that temperature is super hot coming from the stove. Usually it's around 100 degrees Celsius and it can burn. But if it's high enough, it's going to be cool almost to the temperature of the surrounding. That's why it's expanding in here. So when it rises, super hot, compressed, and as it expands, it loses energy to the environment and cools down, okay? So that is basically how one way of getting rid of heat is through basically this process. And this will bring us to the idea of respiration also, which is an important way of cooling down. What happened in here? I live near the hospital, so if you guys hear that, let me see. It went out. Sorry about that. Anyway, so basically, again, that is one way of actually losing energy in this case, but through expansion. And this is exactly the process through which that happens, okay? So opposite to warming. And this is, again, how the process of convection is. So let's look at it again in here in terms of the weather phenomenon. Water has a very high specific heat, okay, compared to solids, compared to, for example, soil, okay? So what happened in this case is during the day, the air is warm, okay? Since it's warm in this case, it's not going to, the heat is actually absorbed the same amount of heat both by the surface and actually by the water. Both of them are the same heat. So if there is, for example, 100 joules, which is just a example, being absorbed, 50 of it will go to here, the water, and 50 of it will go to the soil. However, because of the high specific heat of the water, that 50 joules will only raise the temperature of the water only very little. Relatively speaking, this one has very low specific heat. That means the temperature will rise higher, okay? Will rise higher. The amount of heat that is absorbed is proportional to the change in temperature and also proportional to the specific heat. Since the specific heat is high here, the change in temperature is low. Since the change in temperature, the specific heat is low, the change in temperature is high. So the land will appear warmer in this case. This feels warmer. So there is a breeze that comes from the ocean, bringing that air with it, which warms it, and then it rises, and then it falls, and this is the cycle during daytime. At night, it's the opposite. Again, the temperature, because there is no heat in here, so heat is escaping, actually 50 joules is escaping and 50 joules is escaping. How much temperature will drop in this case for that same amount of heat that is escaping will depend only on the specific heat in here. The specific heat of the water is so high. That means the drop in temperature is so little. So that's why the fluid in this case drops from 65 to 64. So barely you notice that there is a change in temperature in the ocean. Whereas in this case, the specific heat is very low, the change in temperature is drastic. It went from 70 degrees Fahrenheit down to 60 degrees Fahrenheit. It's colder. So the process now reverses, and you can actually look at the flame. You can do a bonfire, and you see the process basically. Which way the flames will go follows the breeze in this case, follows the actual motion of the air. Okay, you will feel still in this case warmth coming from the ocean because of this warmth that is being brought up in here. And this cycle, whereas during daytime, it's actually this breeze that you're going to feel. So again, this has to do with the heat being transferred through this cycle of convection. This is exactly what this convection process is, and it's a reverse process during the night. This cycle is only on this scale, but it's true actually on the entire planet scale too for the weather phenomenon. It plays a major role in moving big masses of air from one region to the other and basically causing all kinds of weather on the planet. And this is true for the planet Earth as much as almost any other planet. So this process is a very important process. And actually, as I explained before, it's an important process also inside the Earth itself. And it's inside the sun too. And it's inside the same thing inside your soup when you're cooking it. The bottom part of the soup is in contact with the heat source that is burning. The top part is in contact with the air. This one is cooler, this one is hotter. So the hot now has less density, so it's going to rise. The cold one has low density, higher density now, so it's going to fall. And this, when it rises, is going to carry with it the heat, which is going to expand of it in here. And then the other one will come down and grab that heat, and the process reverses. And process goes on and on. Actually, you see bubbles. That's what you're going to see. You will see the bubbles. That is what the boiling is. Again, reason warm air rises, warm air expands, becomes less dense, and is buoyed because it's less dense, so it's going to rise because of the buoyancy. air rises until the density equals to that of the surrounding, in which case it will rise no more, and then the process reverses, okay? Radiation is anything like, for example, a light bulb emits radiation, and because of its color, you can see how much radiation in here. Anytime you have flames, you have, for example, your antenna on your phone, your radio, all of them radiate energy in the form basically of electromagnetic waves. So it is a wave really of electricity and magnetism moving in empty space. And that is basically what it is. Our eyes are only sensitive to a very tiny range of them, from the red region to the violet. And that is what our eyes see. But there is actually frequencies that are much higher than the violet, called ultraviolet, and even higher than that are the X-rays, and even higher than that are gamma rays. And there are frequencies lower than actually red, which are called the infrared, and then actually lower than that are microwaves, and there are frequencies that are lower than that, which are radio waves, okay, and even longer than that, as a matter of fact, okay? So there is all kinds of waves. So again, it's a wave. So you create a pattern here. This is a string, a wave on a string, just to explain what the idea is. Low frequency, high frequency, high energy, low energy, okay? So it's worth remembering this in the discussion in here. So here, low frequency, low energy. This is item 2 of the discussion, by the way. Long wavelength. This is the wavelength for this wave, okay? It's in meters. Whereas this is the wavelength. It's a short wavelength. So in this case, it's a high frequency, high energy, short wavelength. So this is the characteristic of radiation. This what characterizes the radiation. Item 2. Okay. So radiation is an important aspect. We happen to see only in a narrow range on it. Our eyes are sensitive only to a narrow range on it. They span from red to violet. Anything below that is the infrared, the microwave, and radio waves, which are used actually for your cell phone and your TV and all of that. Your remote control is in here somewhere. Okay, your cell phone is in here somewhere. That is actually the communications. And then you have UV radiation, ultraviolet radiation. You have X-ray radiation. Those stuff that is your we're going to learn about this more down the road. X-ray radiation is used by technicians in the lab. Your super energy. It could cause a lot of problems. UV actually can cause still a lot of problems. They can kill life on Earth if there are too much of them. So they can kill you too. So if it's a small amount of it, you can see basically your skin starts to change, okay? X-ray can kill you definitely. Gamma rays, they are actually worse than this. So that's why I was saying this is high energy, high frequency, short wavelength. This is on the opposite side of the spectrum, low energy, low frequency, a long wavelength, okay? So that is basically the spectrum. Our eyes were conditioned somehow to see things in this range and this range only, okay? All of this is radiation. Everything is radiation. The color depends on where you sit in the spectrum. For example, we glow naturally in this region, okay? That is, if we have goggles, we can see a person from a distance, even at night, with goggles. All animals actually in this region. Everything actually, even this cup in here, room temperatures in this region. Things that are hot like the sun, the sun glows right around the green, okay? But we can't see it green because all of the colors are mixed there. We see it white color, okay? And then some stars, they glow actually much higher temperatures than the sun, others lower temperature than the sun. And that is basically what radiation is. It transfers in, not the vacuum. So again, emission of radiant energy, every object above absolute zero radiates anything. So if somebody tells you a radiant, they are not wrong, because everything radiates as long as it's not at 0 Kelvin. At 0 Kelvin, nothing radiates. And there is no such a thing, 0 Kelvin. Doesn't exist. Okay? Since it doesn't exist, basically everything radiates energy. It doesn't matter. From the sun's surface comes light or solar radiation. From the Earth's surface, terrestrial radiation, that is basically the Earth itself is warm, so it's going to radiate energy. So everything radiates, including you and I and everybody else, okay? Mr. Trump radiates too, and so is Mr. Biden, okay? So it doesn't matter which way you are in terms of politics. Both of them are good, okay? Anyway, so again, a low temperature source emits primarily low frequency, long wavelengths. So again, we talked about this one. This is item 2 of the discussion. Low frequency is long wavelengths, okay? A medium temperature in this case is going to be medium frequency and medium wavelengths. And here a high temperature source emits primarily high frequency and short wavelength, okay? That was the item of the discussion. Here is something that is known as the emission of radiant energy in this case as a function of frequency, okay? Usually we plot it as a function of wavelength, but that's fine, okay? So a peak frequency in this case is actually inversely proportional to, proportional directly to the temperature. As the temperature increases, the peak shifts. This is called Wien's law, okay? So the frequency in here for 1600 Kelvin is lower than that of 2400 Kelvin, which is lower than that of 3200 Kelvin, which is hotter object we see in this region. So we cannot see something that is a 1600 Kelvin. So because mainly its radiations is in the infrared region, so we cannot see it, okay? Something that is 2400 Kelvin, we barely see some of its color because only this range that is visible, and even this range is probably of frequencies that we can see. No, this is a visible light. So we're gonna barely see something 2400 Kelvin. Something 3200 Kelvin that is super warm, we're gonna see this much of it. We're not seeing the rest of it. We're not seeing the peak, let alone anything else. Something that is hotter like the sun is gonna be peaking around like this. I'm sorry, like this. I'm sorry, I'm trying to draw something in here. Okay, so we see it in the visible mainly. Okay, that's the sun. Because it's the sun is 5500 Kelvin. So that is the T of the sun. So we see it because it's super high, okay? And it's mainly emits in the visible. Probably our eyes were conditioned because of the sun, not the other way around. Our eyes evolved to some extent to see the peak of the sun because the sun is peaked around this region. Okay, emission and absorption. The surface of any material both absorbs and emits radiant energy. When a surface absorbs more energy than it emits, it is a net absorber. And when it tends to, and temperature tends to rise. When a surface of an object is more than it absorbs, it is a net emitter, and the temperature tends to fall, okay? So emitting radiation is a way for it to get rid of that excess energy, basically, okay? That's how basically you can think of it. And every object, it doesn't matter what it is, it has a coefficient of absorption and a coefficient of emission, okay? An object that emits more than it absorbs is an emitter. An object that absorbs more than it reflects in this case is net absorber. So that's basically for the emission, okay? So an object that radiates or reflects everything in this case is going to appear white to you because it reflects all the radiation, it reflects all the colors, basically. So in this case, the colors they mix in your eye and give you the impression that the object looks white. Whereas an object that absorbs every single frequency in this case, you cannot see, you see only its surrounding because it's emitting back, but you don't see the object itself. So it appears dark in this case because contracted with the background, that's all. Because you're not getting anything out of it, basically. You're not getting anything out of this one, but you're getting stuff out of its background and some parts of it, in this case in here, the spoon or whatever that is. And you make an image of that object in your mind based on the surrounding of the object, what the rest of the surrounding of that object makes up. And then you look at there and you will see a black region of it. And that is basically what's going on in this case. So this is a good observer. That's why the people, the dwellers of the deserts, usually like to wear what kind of color? What color usually they wear? Is it black? Black will absorb all the heat from the desert and they will feel warmer. Is it black clothes or white clothes?
Oh, it's the white ones because they don't absorb heat very well. They're more reflective.
Yeah, that's white. Thank you very much. Are you convinced now, Alisa? Okay, very good. How about Tim? They usually wear white because of the fact that it reflects the heat outside, it reflects the radiation, and they don't get as much heat inside. Good, Tim? I mean, you had the correct reasoning, but I think the conclusion was wrong.
Yeah, correct. I agree with you, Professor. Sorry, I was muted.
Okay, very good. Thank you. Okay, so that's why if you look at them, they usually wear white because of the same reason in here. If you are actually in a place that is too cold, you would want to wear dark clothing to keep you, to absorb the heat that you would, whatever little heat you get to stay cool in this case. Although there are different mechanisms now, we use insulation for other things too. So the color doesn't really matter much, honestly, nowadays with different kind of mechanism for insulation. Again, okay, that's good. Okay, whether surface is a net absorber or net emitter depends on whether its temperature is above or below the surrounding. Again, I talked about that when we were talking about Newton's law of basically cooling. So it depends on how much you emit and how much you absorb. So again, in the winter, because the surrounding is cooler, so in this case, you're going to emit energy and you're going to feel cool because of the fact that you're losing energy. Your temperature is getting less and less, your molecules are moving less and less in this case. So you're going to be a net emitter. But in the summer, the surrounding is hot and you're cooler. So in this case, the heat is being absorbed from the outside to you, and you're going to be a net absorber, which means your temperature is going to increase because your parts are going to be moving faster and faster now. Okay, a model that is used by physicists called the black body radiation, and the black body radiation was just to look at this kind of phenomenon. How can we explain this? So this is really a model, not a real thing, okay? So reflection of radiant energy darkness is often due to reflection of light back and forth many times. So basically here is what the model is. This is a model. This is not a real thing that you can do in the laboratory, even in the laboratory. So you take a box, okay? And you poke a small hole in it, and the surface, the inside surfaces of it are made of metals, perfect reflectors. So in this case, if a ray comes in, it's going to go in, and it has nowhere to go because it's going to bounce back and forth. These are not absorbers, they're reflectors. So the ray in this case is trapped inside, okay? So this is a perfect absorber, okay? Which means that if I reverse the process, it's gonna be a perfect reflector. So this is why we were actually interested in this mathematical model trying to understand what's going on with the radiation. This led to the discovery of brand new physics, and actually the discussions there are interesting. So the mathematics is beautiful, and actually led to Mr. Planck, who came up with a theory to explain how objects emit and radiate energy, and his work he himself did not believe it, of course. But at the end, his work led to the new discovery of new mechanics called the quantum mechanics. And at the end, he won Nobel Prize basically for discovering this thing. Well, he himself was not convinced that it's correct, but at the end, it turns out to be a major, major discovery in physics. Okay. Again, we talked about Newton's law of cooling. It depends on how much gradient in temperature, how much difference in temperature. I gave the example between liquid at 0 degrees Celsius and at room temperature versus if I take the same liquid and put it in the summer sitting at 34 degrees Celsius, for example, this will cool a lot faster, or warm a lot faster, I'm sorry, if I go from this process this way than if I do it this way, okay? Same thing if I want to take ice and try to cool it versus if I take, for example, this much and try to cool it, this will, the speed with which it cools this will be a lot faster than if I take it from this one. So that's basically what this law is. It depends also on the amount of stuff that I want to cool or warm. That is also an important concept in here. This is an interesting experiment we used to do in the lab. It's fun. Again, Newton's law of cooling applies to the rate of change objects cooler than its surrounding warms up at a rate proportional to delta T. Delta T, when you see the symbol delta, by the way, that means difference or change. Delta, that's how you read it. Difference or change. That's just a Greek letter that is used to. Okay, again, the greenhouse effect, we talked about it briefly. Radiation of all wavelengths are absorbed and they can be transmitted through different surfaces like the glass, for example. Glass is a perfect transparent for different radiation, for for short wavelength radiation. That's why I can see the tree outside. Okay, I cannot see it from this side because there is a wall. The wall is an opaque medium when it comes to visible light. Okay, I'm glad there is this wall because people are probably not watching me now, probably walking in the house. Same thing. The window in this case is transparent for most of the radiation, except the long wavelength is not. It's an opaque. It's just like basically this wall. So what happened in this case, radiation goes through, it's absorbed by the material, flowers, sand, whatever in this case. And when it's emitted back, it's not emitted in the same wavelength. It's emitted in a longer wavelength, in which case the glass will return it back or push it back. So this is what we mean by the greenhouse effect. So the greenhouse effect in a nutshell is the process that involves 3 stages, basically. Radiation goes through because it's long wavelength. And in this case, the material itself is transparent. Absorbed by the whatever is inside, the soil, the plants, whatever, the pot in this case, everything. So now it's absorbed by those materials and it's warmer for them, so they're going to emit it back. The temperature they emitted back is not that high. It's not like the temperature of the sun that can send you this short wavelength. They're going to send back only, they're not actually super hot. They're not 5,000 Kelvin. They're only probably 300 Kelvin, which is room temperature. So they're going to emit actually back, but they're going to emit only in long wavelength. That long wavelength now, so this is the second stage of the process. This material now, as far as it's concerned, it's an opaque. It's going to reflect back that thing. Okay, it's going to reflect it back. So you're not, so the energy now is trapped. It doesn't go anywhere. Okay, so there is more coming. Actually, some of it is actually leaving outside because you can still see the plant in here on the glass, for example, but not as much as came in. So there is a net in here absorption. So this is actually a net absorber of energy. Okay. So understanding the greenhouse, again, for the entire planet is going through a greenhouse effect, basically. The greenhouse, it's like a big greenhouse, same thing. You have the atmosphere that is made up of materials that basically made up of CO2 mainly and H2O, which are big greenhouse elements. So this too, as far as the short wavelengths, they're transparent. We can see the sun, for example. We can see the moon because of over these things. But when we reflect back from the Earth, we reflect in long wavelengths, and this acts like the same thing as the glass. They reflect this radiation back. trapping this excess of energy. Some of this radiation that is reflected actually will go through, but it's very little compared to what is reflected. So in this case, we have a greenhouse effect. This is exactly what's going on Venus, for example. Venus has the same problem. Venus has a huge cloud, I mean, atmosphere much more denser than the Earth's, and it's mainly carbon dioxide. Okay, so Venus has a big problem versus, for example, Mars, which does not have any. Mars during the midsummer can be super warm, actually. It can be at room temperature. It can be about 30 degrees Celsius, about 80 degrees Fahrenheit or something. But when it's colder, it can be super cold too, minus 50, minus 70 degrees most of the time, which is super cold. So Mars doesn't have any of the gases, so doesn't have anything. So the greenhouse effect is good to some extent, but not too much. So without the greenhouse effect, the Earth would not have had life on it to begin with, and plants would not have been able to exist. But not too much. Too much will make us like Venus. Too little will make us like Mars, and both of them are bad. Okay, again, this is the planet. This is what I was talking about, short wavelength. Some of the long wavelengths, they go back. Others, they're trapped, and they come back, and that's what causes the rise in temperature on the planet. Okay. So this is real, okay? There is studies that follow this, the temperature, depending on basically as a function of the human activity when it comes to basically industrialization and release of mainly these two things in the atmosphere, especially carbon dioxide. And that is really what seems to be causing this thing in here. So there is a correlation. There is a one-to-one correspondence. But the greenhouse effect, if we don't take care of it, and the more consumption of materials that emit these gases, especially carbon dioxide, because water is going to be recycled somehow, and carbon dioxide is very hard to recycle. Now there are different theories of how to basically recycle it, and it's very hard. Short of plants, it is very costly and it's very hard. The best way to recycle carbon dioxide is through plants, actually, okay? And with deforestation, that is actually happening at a faster and faster rate. Okay. Phase transformation, again, I explained it in the introduction. Those are the main three forms of matter that we see on Earth. We see solids, liquids, and gases. If you put more energy in the system, like for example, through heat, okay? Solid will change into a liquid, and liquid will change into a gas. If you remove energy from the system, the gas will convert into a liquid, and liquid can convert into a solid. So this is basically what we mean by phase transformations in here, okay? So matter exists in the three common forms, solids, liquids, and gas. A fourth phase of matter is plasma, okay? Please do not confuse this word plasma with what biologists and at least medical community uses. That has nothing to do with that. Actually, it's a very violent, different kind of form. You can see it in the lightning. You can see it in the flame. Okay, in fire, that is plasma actually too. So what you saw earlier, that was actually the plasma state. Okay, so this is the plasma state. It's in here, in those flames, okay? Okay, so that is the plasma state, but not, so you saw in this cup in here, the ice, and actually it melts a lot of it now. I don't know if you can see the fluid or not. So liquid, and so those are the three mainstay forms on Earth, but there is actually a fourth one that is lurking out there, okay? And it's actually the main form of matter in the universe. So again, the evaporation is a way for the system to lose energy actually too, okay? That's why you perspire, okay? So again, you take this one, when you move it out, in this case, it's going to evaporate. Condensation is the opposite to evaporation. So again, you have a phase transformation, in this case, from liquid to gas, and from a gas to liquid, okay? So molecules in liquid move randomly at various speeds, continually colliding with one another. Some molecules gain kinetic energy while others lose kinetic energy during the collision. Some energetic molecules escape from the liquid and become gas. Okay, so they lost a lot of their energy. And average, so the system in this case loses energy in that form. Okay. average kinetic energy of the remaining molecules in liquid decrease, resulting in a cooler. Because you have a closed system. While they're colliding, one hits the other, one gains, the other one loses. So the system gains nothing or loses nothing because one of them gains, the other one loses. And at the end, the system itself has nothing to gain or lose. But if one of them escapes with that excess energy, now the system all of a sudden has lost energy. Okay? The system went down in energy because of the fact that that molecule escaped with whatever kinetic energy it has. Okay? And that's what animals do in general, humans too. Okay? So perspiration in this case is a way for you to cool down. Okay? Have no sweat glands and therefore cannot cool by the evaporation and perspiration. Instead, they wallow in mud to cool themselves. Okay? So you put some mud and water around you, and that water will evaporate ultimately because of the heat outside, and takes with it the energy that is in contact with your body. So that's another way of cooling down. That's why if it's too hot, just jump in the swimming pool and come out and it's going to feel better. Okay? But if you do it through perspiration, that is actually one way of doing too. That's why you perspire, trying to getting too hot inside. That's basically why. When you exercise and you do a lot of exercise, it's the same thing. Okay. So it's sublimation is you're going straight from gas to liquid, like for example, dry ice. Okay. If you have ever experienced with it, mothballs and frozen water. So you have a mothball with the clothes, for example, you put it in there and it goes from, it doesn't melt, it doesn't liquid, it doesn't become liquid, it goes straight from solid to liquid, and that's solid to gas, and that's why you smell it. Okay. Frozen water also does that too. Frozen water goes directly. Actually, there is a point in for the water, it's called the triple point, where the water changes from liquid to solid, and or vice versa, from solid to liquid, and solid to actually to gas too. Okay, it's called the triple point of water. Again, condensation is if you're chilly outside to the shower stall, step in, back inside and warm by. So again, this is the reverse process. So the condensation in this case will bring more energy to your system. Okay. I was going to get this toy. Actually, I have it, but I don't know what it is right now. It's basically another way that looks like a. The system is going forever and ever and ever. If you have seen that, if not, actually they sell it not too expensive too from Amazon if you have your hands. So basically, the nose in this case was warm. I mean, it was actually it has liquid in it. So as it peaks inside, it has liquid. Now the fluid moves around. As it moves around, it's warm, so it expands in this case. So it's going to move back to this position. Now it moves back. So this is a cycle, actually. You go from A, B, C, D, and back to A, and so on and so forth. You can take it wherever you want to. So there is a fluid in this case that is evaporating. And as it evaporates, this one will rise in the temperature because it's losing energy in this case. So, and then it's going to repeat the whole cycle again, okay? Oh, what are we doing on time? Still about 10 minutes, and I think we can finish this quickly. So the boiling, I explained basically the process in here. So rapid evaporation occurs beneath the surface of a liquid. So pre-surface pressure of atmosphere plus water. So basically you need the pressure too for the evaporation for the boiling to happen, okay? So when you have less pressure, the boiling point drops down a lot. That's why it causes basically problems, for example, with the case of planets like Mars. Mars, for example, if you put water on it, it's going to boil immediately, even at those low temperatures. So this is the same phenomenon here. We're explaining the boiling in here. So again, boiling, evaporation beneath the surface forms bubbles. Bubbles rise to the surface. If vapor pressure is less than the surrounding pressure, the bubbles collapse. Hence, bubbles don't form at temperatures below boiling point when vapor pressure is insufficient. Again, this is basically the boiling process. You're taking heat from below and you're extracting it to the bottom, to the top, and the bubbles form, and then they rise and they collapse, and the whole process repeats again and again and again. The pressure cooker is actually happening at the same volume. So you're trapping the formation in here. So it's happening at high pressure. So in this case, all of this gas is basically feeding itself through this process, trying to keep its while getting heat in here from bottom still, okay? So the temperature rising and rising, in this case, when the pressure is rising too. That's why it's called pressure cooker. Okay, I know I did not, okay, the points in equilibrium in here, this is, I mentioned the triple point for the case of water. Again, the water has this peculiar property. When it cools down, it expands, which is kind of opposite to what most materials do. Most materials, when they cool, they collapse, their density increases. The water, its density actually decreases, goes down. That's why ice doesn't sink, it floats. Okay, if you look at an iceberg, for example, you will see it actually sitting on top of the ocean. Okay, it's not all of it sitting on top of the ocean. It's still about 90% of it is below the ocean. And again, because of this property of the water for the case of the water. In here, there is an interaction between the molecules themselves. You have a water molecule, which is H2O, another water molecule, which is H2O, and because each hydrogen basically loses an electron to the oxygen atom, the oxygen atom will bring closer, actually doesn't lose it, but bring closer those electrons to it than if they would be next to the hydrogen atoms. So in this case, what we have a netted charge, a positive charge on one side and negative charge on the other side. And this atom and the one next to it, they have an interaction. This is called the van der Waals force, basically, where you have as if charges on one side, positive and negative on the other side, interact one another. This interaction doesn't last over long distances, just short distances between the near neighbors only, okay? Between this water molecule and this water molecule, and probably this one too. But this one, for example, doesn't influence this one. There is no order in here. So that's why you have a liquid. When it cools down to below freezing, in this case, actually, they rearrange themselves so that the oxygen faces the hydrogen and the hydrogen faces the oxygen. And now you have actually an electrostatic force causing them to rearrange, and they rearrange themselves in this fashion, causing the spacing between them to increase. As the spacing increases, now the density becomes lower. It's the same amount of atoms that you start with. If you have 10 atoms before and 10 atoms now, so the number of atoms did not change, but the spacing between them is bigger in the case of a solid versus when it's liquid, causing the density to go lower because you have the same amount of stuff, but now in a bigger volume versus in the beginning, which is the same amount of stuff in the more compact volume. So that's why the water is actually more liquid. Water is more dense than ice water, okay? And that's why the ocean, basically, if you go around it, and if I put water in here, actually there is water right now. The water is actually in the bottom and the ice on the top. Had it been the opposite, had the density of the water been less than the density of the solid should sink to the bottom of the cup, and that is not happening. And it's a good thing that this is the case for the case of water because it has this particular property. That means that ponds and oceans in general do not freeze from the bottom up. They freeze from the top down. If they freeze from the bottom up, then we have a problem. They start freezing and they never stop. Then all the oceans will be solid, basically ice. There cannot be life in the oceans, which means there cannot be life on Earth because it's going to cool down indefinitely and it's going to be really an icy world, which is really bad too. So you don't want it to be too hot. You don't want it also to be frozen solid. That's not good. So the fact that the water has this property is actually a good thing because it lets marine life to evolve in the ponds and oceans and everywhere else, and that's basically what allows it for that to happen. Again, ice is not all of it actually above the water. Some of it will go below. It's about 90% of it. So if you see that there is an iceberg at the bottom, there's a lot more of it immediately underneath. And that's what caused those people to die. Remember in the story, the movie? Yes or no? Did anybody watch the movie?
Titanic?
Yes, okay. So that's exactly what went wrong with them because they failed to realize that there's a lot of ice actually underneath. So I guess they didn't see it, okay? Anyway, so I guess we're done with chapter 7. Hopefully you guys will go through the materials again, okay? And review this stuff. you'll have an opportunity to really take the review far more in depth this Thursday for chapters 1 through 7 and go through them, print them if you like, go revise them, understand what's going on. You can't print, that's too many pages, okay? It's about 20, no, actually about 30 something pages, okay? So don't do that. So just go through the materials one by one, look at them, make sure you understand them, and please take it seriously, okay? Do not leave it to the last day and say, oh, tomorrow I have an exam, so I better do that review. That is bad strategy. So I would recommend if you can start with it, let's say Friday. I hope you start on Thursday, but if you cannot start with it on Friday, the latest you should start on it is on Saturday, okay? Saturday, dedicate at least good 2-3 hours on it, understanding every single question. And then if you still have doubts, come back to it again and make sure you have everything clarified. Still, there is a confusion about specific question or questions, send me an email, shoot me an email. Don't leave it until Sunday afternoon and send me the email because it's too late. So please send it as soon as possible so that I look at it and tell you, yeah, it makes sense, or maybe there is something wrong with that question or that thing in there, okay? So this is the plan. I will see you guys on Thursday because we have a brand new chapter, chapter 8, where we're going to talk about electricity, which is not due for this exam, but is due for the next exam, which means that we have to take it also seriously too, okay? Please ask questions. I have, we have about 3 minutes or so. If you guys need anything right now, otherwise, please send the questions via Canvas and hopefully I will answer them. I know sometimes I don't get right away to the answer, but hopefully I'll get soon enough. This Friday, Friday is the 12th. We have actually a very big event planned with the STEM Center. I'm hoping some of you will take advantage of it and participate, which is due actually the 11th. It's for the Mars Challenge, for the Mars Lander Challenge. So hopefully some of you will try it. It's with eggs and try to throw them and make sure that they stay safe and record it with your phone. If it works, just upload the thing. If it doesn't work, just upload the thing still, okay? And come on Friday also to meet with us and have fun discussing these things and all the things and projects in the future, okay? Good?
Question, Professor. For the item 2, did you wanted us to just state the differences between the radiation frequencies, like the vibrations?
Yeah, I want you to basically, okay, I took the wrong thing in here.
Yeah, you restate the 2 questions for the, because I know it was like the radiation of high frequency and low frequency.
Those things in there, okay, because it's important to know that the low frequency is low energy, is long wavelength, okay? High energy, high frequency, short wavelength, okay? This is something that probably is good to remember after this class. So you don't want to be Googling these things, okay? The energy and the frequency, they go 1 and 1, whereas the wavelength is opposite, okay? So high frequency is actually short wavelength. Low frequency, which means low energy, is actually long wavelength. That is the key that I want you to really come up with and have a full understanding that there is this correlation between energy and wavelength and things like that. So that when you're looking, reading something online, or you're listening to the news, or something about UV, you have the visualization of what's going on, of what is that they are talking about, okay? Oh, Andrea, the first question about the different phases of matter in the universe and which one is a dominant. Is that the answer to the question, Andrea?
Yes. Yeah.
Okay. So I'll see you guys Thursday, okay? I have another class that starts in about 3 minutes. Let me stop recording.